Hello everyone, I hope you're having a great day today. So today we're talking about fats and the ergogenic aspects. Looking at chapter 5 and part 3. So because exercise training leads to an increased utilization of fatty acids as an energy source and improved performance in prolonged endurance events, theoretically by sparing muscle glycogen, a variety of dietary practices, dietary supplements, and pharmacological agents have been employed in an attempt to facilitate this metabolic process during exercise. Both acute and chronic dietary strategies have been used to increase the concentration of muscle triglycerides or serum level of free fatty acids or FFA. Such strategies include high-fat diets, fasting, and even infusion of lipids into the bloodstream. Dietary supplements and drugs have been used to either increase the supply of oxidizable fats or the rate of fat metabolism. Dietary supplements include medium-chain triglycerides, lecithin, glycerol, omega-3 fatty acids, carnitine, hydroxycitrate, conjugated linoleic acid, and phosphatidylserine. Caffeine also has been theorized to enhance fat oxidation and its role as an ergogenic aid and is covered in chapter 13. So high-fat diets are among the most popular and controversial diets in nutrition. First, a great deal of research points to diets high in fat as disease-promoting. This will be discussed later in the chapter. Second, if one macronutrient is increased and calories are held constant, the amount of another macronutrient in the diet must decrease. The beneficial effect of high carbohydrate diets on exercise performance, as described in the previous chapter, has been well documented. So, if an increase in dietary fat results in a decrease in dietary carbohydrate, performance could be compromised. High-fat diets may be used on an acute or chronic basis. Some people prefer or refer to acute high-fat diets as fat loading. Acute high-fat diets, as lipid digestion and absorption are slow, so one strategy is to infuse a lipid solution such as intralipid directly into the blood along with heparin, a substance that stimulates lipoprotein lipase activity and increases plasma free fatty acid levels. Such a strategy increases fat oxidation and reduces carbohydrate oxidation, which may enhance endurance exercise performance. However, after a lipid solution was used by a national team in the Tour de France, the entire team withdrew from the race allegedly due to adverse reactions. No research has been covered that supports this ergogenic technique. A second strategy is to ingest a high-fat meal prior to exercise performance. For example, in 2 studies, Okano and others reported no significant differences between a high-fat meal of about 61% fat and a control or low-fat meal on performance in a cycling test to exhaustion at 78 to 80% VO2 max following 2 hours of riding at 60 to 67% VO2 max. An acute high-fat dietary strategy does not appear to enhance performance and in fact may actually impair performance if it contributes to gastrointestinal distress because of the delayed gastric emptying associated with fats. Research has shown that consuming a high-fat diet for 1 to 2 days, another acute approach, may actually impair performance in high-intensity exercise tasks. One of the principles behind keto adaptation is that athletes must be consuming high-fat diets for long enough to gain an effect. Thus, the lack of a benefit seen on exercise performance in studies of acute high-fat diets is not surprising. Several investigators have challenged the dogma that endurance athletes need high carbohydrate diets and suggest that endurance performance may benefit from diets containing about 50% or more energy from fat. In general, research has shown that when an individual is placed on a chronic low carbohydrate and low-fat diet for about a week or more, the body adjusts its metabolism to use fats more efficiently. However, metabolic improvements do not necessarily correlate with or guarantee performance improvements. There are studies showing ergogenic effects. Several of the studies support an ergogenic effect of chronic fat loading. Pendergast and Harbaugh, along with their associates, conducted several of the first contemporary studies. Although 2 studies from their laboratory have shown that adapting to a high-fat diet of about 38 to 41% fat content over a 1 to 4 period improved treadmill running time to exhaustion. Both studies had problems with the experimental design, such as no random assignment of the diet conditions and no counterbalancing of diet order. Moreover, the diets were not exceptionally high in fat content. Muyo and others acknowledged the limitations to experimental design in their prototype study, and the interested reader is referred to the other study by Vincontriman and Pendergast. More recently, Harbaugh and others had male and female runners consume diets of 16 and 31% fat for 4 weeks, and then about half the subjects increased their dietary fat intake to 44%. All diets were designed to be isocaloric, but the runners actually consumed about 19% fewer calories on the low-fat diet. There were no differences among the diets for VO2 max, anaerobic power, or body mass, but the endurance run after the low-fat diet was reduced compared to the medium and high-fat diet. However, it is possible that decreased energy intake contributed to this decrease in performance. Lambert and her colleagues also found ergogenic effects in several studies. In one study, they placed athletes on a high-fat or 70% fat calorie diet or low-fat 12% calories diet for 2 weeks, testing the effects on 3 performance tests done in consecutive order with 30 minutes rest between each. The 3 exercise tests included a Wingate high power test, a high-intensity test to exhaustion at 90% VO2 max, and a moderate-intensity test to exhaustion at 60% VO2 max. Although there was no significant effect between the 2 diets for performance in the first 2 exercise tests, the cyclists rode significantly longer on the moderate-intensity test, following adaptation to the high-fat diet. The investigators noted that adaptation to the high-fat diet decreased the reliance on carbohydrate as an energy source during exercise, and thus suggested the improved performance was due to muscle glycogen sparing. Conversely, other well-controlled research suggests that chronic high-fat diets do not benefit endurance performance. The most often cited study used to argue the beneficial effects of a low-carbohydrate diet, high-fat diet on endurance performance was established or published in 1983 by Finney and colleagues. After 4 weeks of keto adaptation, there were dramatic increases in fat oxidation, on average about 90 grams per hour, and decreases in exercise RQ from 0.83 to 0.72 in 5 cyclists. Interestingly, pre-exercise muscle glycogen levels at the end of the study were half of what they were at baseline. However, there were no changes in VO2 max and no improvements in endurance performance as a result of the diet. Using well-trained cyclists as subjects, Havanen and others reported no significant differences in 100-kilometer time trial performance when consuming either a high-fat diet of 68% fat or a high-carbohydrate diet of about 68% carbohydrate for 6 days, followed by 1 day of carbohydrate loading. But the high-fat diet impaired 1-kilometer sprint power. The authors noted that although the high-fat diet increased fat oxidation, it compromised high-intensity sprint performance. Several studies have shown no effect of chronic fat loading on endurance performance in trained individuals. Brown and Cox, in a randomized study using 32 endurance-trained cyclists, reported no difference in 20-kilometer road time performance over a period of 12 weeks when subjects consumed either a high-fat diet or a high-carbohydrate diet. Burke and her associates found no beneficial effects in 2 studies. In the first study, they investigated the effects of a high-fat diet for 5 days, followed by a 1-day high-carbohydrate diet on an endurance cycling protocol, involving cycling at 70% VO2 max for 2 hours, followed by intense time trial. Compared to a high-carbohydrate diet, the high-fat diet induced greater utilization of fat with an associated muscle glycogen sparing, but there was no significant improvement in the cycling time trial, even though performance following the high-fat phase was about 3.4 minutes faster. In a subsequent study using a similar protocol, Burke and her associates reported no significant impact on endurance performance. In a crossover design study, Holloway and others recently placed healthy men on a 5-day diet of high fat, 70% fat, 4% carbohydrates, and 26% protein, and a control of about 24% fat, 50% carbohydrates, and 26% protein. Men in the study ingested one diet and following a 2-week washout period consumed the other diet. The high-fat diet impaired cognitive function in the areas of attention, speed, and mood. A decrement in any one of these areas could affect an individual's ability to train and compete, particularly in activities that require an athlete to react to an opponent or conditions. So the bottom line is overall research findings are equivocal, but generally indicate that a chronic high-fat diet does not enhance aerobic endurance performance. Endurance athletes may actually adapt to high-fat diets, but training becomes more psychologically stressful. And endurance performance can at best only be maintained on such diets as compared to high carbohydrate diets. You may also see that it impairs their endurance performance as well as their cognitive function. Diets containing about 20 to 30% of energy from fat appear to be reasonable for endurance athletes. Now, does exercising on an empty stomach or fasting improve performance? A controversial area related to dietary fat intake is the issue of fasting for a limited period of time prior to exercise. Some people contend that this will improve training adaptations and subsequent performance. Indeed, fasting, even an overnight fast, can increase free fatty acid availability and theoretically increase fat oxidation, spare glycogen, and improve performance. On the other hand, if fasting reduces muscle glycogen or causes hypoglycemia, it could impair performance. Another popular theory is that training while fasted will encourage greater weight loss, either through metabolic adaptations or reductions in appetite. Despite the large amount of available research on the benefits of carbohydrate ingestion before exercise, several research groups have examined exercise after various durations of fasting. Following is a summary. Gutierrez and others reported decreased aerobic endurance physical working capacity in young men following a 3-day fast. Data from Peter Hespel's lab showed that following a 6-week endurance training program, training in a fasted state increased oxidative enzymes such as citrate synthase and B-hydroxyl coenzyme A dehydrogenase and intramyocellular lipid breakdown more than training in a fed state. Other work from this group showed that GLUT4 and proteins involved with the fatty acid transport increased when training in the fasted state. However, following the endurance training program, there were no differences in VO2 max between those who train under fasted or fed conditions. Standard and colleagues compared 4 weeks of fasted or fed endurance training and showed greater increases in VO2 max in fasted subjects and greater increases in muscle glycogen in fed subjects. There were no difference in the citrate synthase and hydroxyl coenzyme A dehydrogenase between groups. The readers caution that beneficial metabolic changes may not lead to beneficial performances. Some believe that training while fasted improves weight loss more than training in a fed state. Schoenfeld and others examined the effects of 4 weeks of training in a fed or fasted state while on a hypocaloric diet. Both groups decreased body mass and fat mass, but there were no differences between the groups. Authors acknowledged that a longer period of time may be needed for any differences between protocols to take effect. In acute studies, both Gonzalez and Dayton showed that there was no advantage of exercising after an overnight fast or after a meal on subsequent appetite or daily energy intake. Thus, there are no convincing data that athletes should train while in the fasted state. However, many Muslim athletes may be training or competing while fasting for religious reasons during Ramadan. Trabelsi and others showed that resistance training was unaffected by fasting during Ramadan, but that fasted athletes were more likely to be dehydrated. In a similar study, endurance training while fasting during Ramadan resulted in changes to various metabolic parameters related to hydration and kidney function, although it is not currently known if sports performance per se is negatively impacted by fasting during Ramadan. Athletes should be aware that proper hydration may be compromised. So can the use of medium chain triglycerides improve endurance, performance, or body composition? It has been suggested that medium chain triglycerides, or MCTs, are ergogenic, possibly because they are water soluble, which may confer two advantages. They can be absorbed by the portal circulation and delivered directly to the liver instead of via the chylomicron route in the lymph, and they more readily enter the mitochondria and the muscle cells as they do not need carnitine. MCTs have been marketed commercially. Research has shown that MCTs do not inhibit gastric emptying as common fat does and may be absorbed rapidly in the small intestines. Also, Mascott and his associates reported that exogenous MCTs are oxidized at a rate comparable to exogenous glucose, being oxidized within the first 30 minutes of exercise. MCT supplements are available as a liquid which can be added to food or soft gel capsules. MCTs are also added to meal replacement powders, energy, and protein bars. Recently, possibly due to an increase in low carbohydrate, high fat diets, or in foodstuffs such as the coconut oil, there has been a resurgence in MCT use. Bueno and colleagues recently completed a meta-analysis of the effects of replacing at least 5 grams of dietary long-chain fatty acids with medium-chain fatty acids in 16 studies that included 399 participants. Reportedly, replacement with MCTs resulted in greater reductions in body mass, body fat, and waist circumference. But the authors stated that their results should be taken with caution until a longer duration and better quality research trials are completed. Mumm and others also conducted a meta-analysis of the effects of MCTs on weight loss and body composition, studying 13 trials with 749 individuals. MCT ingestion resulted in greater decreases in body mass, body fat, and subcutaneous and visceral fat, but these changes were small. Consuming MCTs resulted in about 0.51 kilogram per kilogram extra decrease in body mass over a 10-week period of time. More importantly, the authors systematically identified several areas of concern with the studies they included in their analysis. They expressed concerns over how well the MCT products were blinded, if data were selectively reported, and if there was a commercial bias. Bueno and colleagues also note that the blinding of the source of the fat in their analysis was rated low or unclear for every study. Some early research found that MCT supplementation alone may actually impair endurance exercise performance, whereas an MCT carbohydrate supplement may be ergogenic. Benzil and others using endurance training cyclists compared the effects of 3 supplements on an endurance performance task, consisting of a 2-hour ride at 60% VO2 max, followed by a 40-kilometer performance ride. The 3 supplements consumed throughout the performance task were carbohydrate only, MCTs only, and carbohydrate with MCTs. The MCT dose was 86 grams. Compared to the carbohydrate supplement, the MCT supplement actually impaired 40-kilometer performance, whereas the combination of carbohydrate and MCT supplement improved performance. These investigators suggested that the carbohydrate MCT supplement improved performance in the 40-kilometer performance ride by decreasing oxidation of muscle glycogen during the preliminary submaximal 2-hour ride, thus sparing the glycogen for the more intense exercise tasks. However, most studies have not shown any beneficial effects of MCT supplementation, either alone or combined with carbohydrate, on endurance exercise performance. Is the glycerol portion of triglycerides an effective ergogenic aid? As you may recall, glycerol is one of the byproducts of triglyceride breakdown. Burrell and others have noted that exogenous glycerol can be oxidized during prolonged exercise, presumably following conversion into glucose in the liver. Thus, researchers theorized that it could be an efficient energy source during exercise. However, in well-controlled research, Glycerol feedings did not prevent either hypoglycemia or muscle glycogen depletion patterns in several prolonged exercise tasks. Apparently, the rate at which the human liver converts glycerol to glucose is not rapid enough to be an effective energy source during strenuous prolonged exercise. However, as noted in Chapter 9, glycerol may be used to increase body water stores, including plasma volume, prior to exercise, and has been theorized to be ergogenic for endurance athletes performing under warm environmental conditions. Are phospholipid dietary supplements effective ergogenic aids? Lecithin, also known as phosphatidylcholine, is a phospholipid that occurs naturally in a variety of foods such as beans, eggs, and wheat germ. Because it is an important component of many types of human body tissues, it contains choline needed for the synthesis of acetylcholine, an important neurotransmitter, and contains phosphorus. It has been theorized to be ergogenic. Several German studies conducted more than 50 years ago reported increases in power and strength following several days of supplementation with 22 to 83 milligrams of lecithin. However, these early studies have been discredited because of poor experimental design. In a study with better experimental design, statin reported 30 grams of lecithin supplementation daily for 2 weeks had no effect upon grip strength. If we look at phosphatidylserine, like phosphatidylcholine, it is naturally occurring phospholipid found in cell membranes. Food products that are good sources of phosphatidylserine include green leafy vegetables, rice, fish, and soybeans. Dietary supplements, some marketed as phosphatidylserine, are derived primarily from soybeans and are marketed to improve brain health, claiming to be essential for normal functioning of neuronal cell membranes. Several studies have evaluated the effects of this supplementation on various responses to exercise and exercise performance. Kingsley notes that phosphatidylserine may serve as an antioxidant, which may help reduce muscle tissue damage. It also may help promote optimal balance of calcium and other minerals in the cells during exercise, which might influence exercise performance because of its role in promoting transport of substances across cell membranes. Kingsley also notes early research indicated that oral supplementation moderated exercise-induced changes in the hypothalamic pituitary adrenal axis, which could affect hormonal responses to exercise that may influence performance. In one of the first studies, Kingsley and others provided male soccer players with 750 milligrams of soy phosphatidylserine daily for 10 days. The players engaged in intermittent exercise designed to stimulate soccer match play, immediately followed by an exhaustive run. The supplement had no effect on muscle soreness or markers of muscle damage, and lipid peroxidation followed exhaustive running. However, supplementation tended to increase running time to exhaustion, but the difference between the treatment and placebo groups was not statistically significant. In another study with a similar supplementation protocol, Kingsley and others reported no significant effect of supplementation on markers of muscle tissue damage, inflammation, and oxidative stress, or on delayed onset of muscle soreness following downhill running for nearly an hour. Although lecithin does not appear to be an effective ergogenic aid, several of its constituents have been theorized to enhance exercise performance. Choline, an amine associated with vitamin-like activity, has been associated independently or as part of lecithin for potential ergogenic effects on endurance performance, and is discussed in Chapter 7. Phosphate salts are covered in Chapter 8. Although phosphatidylserine supplementation appears to have little effect on reducing markers for muscle damage or soreness after severe exercise, Kingsley and others did find improved exercise performance in one study using a similar supplementation protocol. There was significant increased cycle timing to exhaustion at 85% max, and the author suggested that phosphatidyl supplementation might possess ergogenic potential. These findings are interesting, but research with phosphatidylserine supplementation and exercise performance is in its preliminary stages and additional research is merited. There is a great deal of interest in the health-promoting or ergogenic effects of omega-3 polyunsaturated fatty acids. It is well known that populations who consume diets high in these fatty acids have decreased risk of cardiovascular disease. In particular, eicosapentaenoic and DHA acid, have been studied because of their potential anti-inflammatory effect. People who do not regularly consume oily fish possibly consume less than 200 milligrams per day, and fish oil supplements are an easy way to increase omega-3 fatty acid intake. With this, the theory is that the omega-3 fatty acids are considered to be an ergogenic aid because they may increase blood flow or oxygen delivery. With the red blood cell membrane being less viscous, it's easier blood flow. And again, they produce the eicosanoids that induce vasodilation, but may also increase secretion of human growth hormone. And it's also one of the theories of the zone diet. Omega-3 fatty acids are theorized to be ergogenic not because of their energy content, but because they may elicit favorable physiological effects relative to several types of physical performance. One theory is based on the finding that omega-3 fatty acids may be incorporated into the membrane of the red blood cell, making the red blood cell less viscous and less resistant to flow. Another theory is based on the role of certain byproducts, the eicosanoids mentioned previously, whose production in the body cells is related to omega-3 fatty acid metabolism. In particular, two specific forms of the eicosanoids, the prostaglandin E and prostaglandin I, may elicit a vasodilation effect on the blood vessels. Walser and others noted that 6 weeks of EPA and DHA supplementation enhances blood flow during exercise in healthy individuals. Theoretically, the less viscous red blood cell and the vasodilatative effect should enhance blood flow, facilitating the delivery of blood and oxygen to the muscles during exercise, benefiting the endurance athlete. Unfortunately, the ergogenic potential of omega-3 fatty acids is an interesting hypothesis. There are a few supportive scientific data. Results from well-controlled, peer-reviewed scientific research indicates that omega-3 fatty acids do not affect energy metabolism during exercise. Can carnitine improve performance or weight loss? Carnitine is a water-soluble, vitamin-like compound that facilitates the transport of long-chain fatty acids into the mitochondria. There are basically two forms of carnitine, L-carnitine and D-carnitine, but other forms are available, such as L-propionylcarnitine. L-carnitine is the physiologically active form in the body, so the following discussion carnitine will refer mostly to L-carnitine, but in some studies, L-propionylcarnitine has been used. Dietary source. Carnitine is not an essential dietary nutrient because it may be formed in the liver from other nutrients, principally two amino acids, lysine and methionine. Also, carnitine is found in substantial amounts in animal foods. Meat products, particularly beef and pork, are good sources of carnitine, but much less is found in fish and poultry, and even lower amounts in dairy products. Only minimal amounts of carnitine are found in fruits, vegetables, and grains. For example, for similar weights, beef has about 300 times as much carnitine as bread. 3 ounces of beef contains about 60 milligrams of carnitine. There is no RDA for carnitine. Most individuals consume enough carnitine in their daily diet, and the body has an effective conservation system. The typical non-vegetarian diet provides about 100 to 300 milligrams per day. Carnitine deficiencies are very rare. The carnitine supplementation has been theorized to enhance physical performance and weight loss because of several of its metabolic functions in the muscle cell. Approximately 90% of the body's supply of carnitine is located in the muscle tissues, where it is part of an enzyme, carnitine palmitoyl transferase, important for transport of long-chain fatty acids into the mitochondria for oxidation. Theoretically, supplemental carnitine might facilitate the transport of LCFAs into the mitochondria for oxidation, which would be an important consideration if the oxidation of fatty acids were limited by their transport into the mitochondria. Although these are logical theories and interesting medical applications, the available scientific evidence is somewhat equivocal and generally does not appear to support an ergogenic effect of carnitine supplementation. Supplementation will increase plasma levels of carnitine, but much of this will be excreted by the kidneys. Other information, the findings are interesting and merit additional research, possibly evaluating the effects of carnitine and tartrate separately. The primary theory underlying carnitine supplementation is enhanced fat utilization. If muscle carnitine does not increase with supplementation, no increase in fat oxidation should be expected. And this has been reported. However, in the study by Wall and others in which muscle carnitine did increase, muscle glycogen use decreased 55%. Muscle lactate was 44% lower, and work output improved. Numerous studies have reported no ergogenic effect under a variety of exercise test conditions, likely because muscle carnitine did not increase in those trials. As the number of studies showing no metabolic or ergogenic effect of carnitine far outweigh the number that have shown an effect, carnitine cannot be recommended until more research is conducted. Both Asker and Jukrup and Melinda Menor, two experts on dietary supplements and sports nutrition, have reviewed the purported effects of carnitine on weight loss. Neither finds any evidence that carnitine is effective for weight loss. D-carnitine may be toxic as it can deplete L-carnitine, leading to a carnitine deficiency. L-carnitine appears to be a safe supplement, but some reviewers recommend no more than 2 to 5 grams per day, possibly for only a month at a time. Carnitine is generally thought of as an ineffective ergogenic aid, but this is probably because it is difficult to increase muscle carnitine. Until a way to increase muscle carnitine becomes available and more practical supplementation cannot be recommended, although more research needs to be done. Hydroxycitric acid is derived from tropical fruit and marketed as a dietary supplement. Hydroxycitrate, or HCA. Cricketose and others noted that as a competitive inhibitor of citrate lysase, HCA has been hypothesized to modify the citric acid cycle metabolism to promote fatty acid oxidation. Although some studies with mice suggest that HCA supplementation may enhance endurance performance, human studies do not support such an ergogenic effect. Cricketose and others in an excellent crossover study reported no significant effect of HCA supplementation of about 3 grams per day for 3 days on blood serum energy, substrates, fat metabolism, or energy expenditure, either during rest or during moderate intensity exercise. However, the subjects were sedentary males using endurance-trained cyclists as subjects. Van Loon and others evaluated the effect of HCA supplementation given twice to the cyclist before and during 2 hours of cycling at 50% VO2 max. They concluded that HCA supplementation, even in large quantities, does not increase total fat oxidation in endurance-trained cyclists. Can conjugated linoleic acid enhance exercise performance or weight loss? Conjugated linoleic acid, or CLA, has been marketed as a sports dietary supplement to resistance-trained individuals, mainly as a means to promote weight loss and gain muscle mass. For example, or for similar and other reasons, CLA has been marketed as a means to improve health. Research regarding its ergogenic effect on exercise-trained individuals is very limited. Using resistance-trained athletes as such, Kreider and others investigated the effect of CLA supplementation on body composition and muscular strength and reported no significant effects on total body mass, fat-free mass, or strength, as measured by a single maximal repetition in the bench press and leg press. Pinkowski and others in a crossover design also found that CLA supplementation resulted in minimal changes in body composition and no changes in the strength tests in males and females involved in resistance training. However, in the first phase of the study, which did not involve a crossover design, male subjects receiving CLA experienced significant increases in bench press strength compared to the placebo group. The crossover phase of the design of the study, as the authors noted, is a stronger experimental design. So what's the bottom line regarding the ergogenic effects of fat-burning diets on strategies? As noted in this section, numerous fat-burning strategies have been employed in attempts to enhance prolonged endurance exercise performance. Theoretically, such strategies would increase the oxidation of fat, decrease the utilization of carbohydrate, and thus spare more muscle glycogen for use in the later stages of exercise. As muscle glycogen is a more efficient fuel compared to fats, performance should be enhanced. However, John Hawley, an international sports science scholar, reviewed all such fat-burning strategies and concluded that endurance exercise capacity is not systematically improved with increases in serum free fatty acid availability, even in some studies with substantial muscle glycogen sparing. He noted that for some reason, exercise capacity is remarkably resistant to change. Other studies suggest that high-fat diets may impair performance in some events, such as high-intensity surges during a race or sprints to the finish. Moreover, individuals may find it difficult to adhere to a high-fat diet. Other key concepts of the fat-loading practices, either acute or chronic, may increase utilization of fat during endurance exercise, but do not appear to enhance exercise or sports performance. The chronic high-fat diets may increase the psychological stress of exercise training, as we discussed earlier. The medium-chain triglyceride or MCT supplementation does not improve and may actually impair endurance exercise performance. Consuming an MCT carbohydrate solution provides no additional benefits compared to a carbohydrate solution alone. Carnitine supplementation does not appear to increase muscle carnitine content. It does not affect oxidation of fat during exercise and does not enhance endurance exercise performance. In general, various dietary strategies and dietary supplements theorized to increase oxidation of fat during exercise and enhance prolonged aerobic endurance performance have not shown to be effective ergogenic aids. So that concludes our discussion.